The lecture is scheduled on remote sensing and GIS applications in soil resource assessment. In this lecture, I will discuss on soil mapping, land evaluation, mapping of degraded lands, and this will be discussed with the use of multispectral satellite data, and at the end use of hyperspectral remote sensing in mapping of soil properties. If we see that is what do you mean by soil? Soil is the most valuable natural resource that serves as a natural medium for plant growth. We know all. Soil is the Latin word and which is derived from the word solum, which means floor. If we see the what is the composition of soil, soil is composed of mineral matter 45%, mainly characterized as sand, silt and clay. Second is organic matter, which is a maximum, which amount may be 5% average. That is the mainly soil carbon present in the soil. Then third constituent is air, which is 20 to 30% in the form of oxygen, which is required for the bacterial and fungi growth and roots respiration, and CO2 carbon dioxide, which is liberated by by respiration. Then water, rest 20 to 30% is water present in the soil. So soil is composed of mineral matter, organic matter, air and water, and that governs the physico-chemical properties of the soil. When we go for the mapping of the soil, and then our definition of the soil becomes slightly technically is oriented towards soil resource mapping. Then we define soil as a natural three-dimensional body at the earth surface, which is capable of supporting plants and has properties and the results and the physicochemical properties that develop into the soils. It is because of the interaction of climate and organism which act on the parent material, and it is conditioned by topography over the period of time. I mean to say, for the soil resource mapping or for the standard soil survey, our concern is for the soil is from the three-dimensional body. You can say we study the soil up to 2.5 meter depth of the soil, or the depth restricted by rock. So up to the rock, which if it is not rock, then we go up to 2.5 meter. If it is rock, then we restrict our depth of the soils up to the rock. So we study that soil as a three-dimensional body. If we see the soil variability, so when we suppose the picture is shown here is that is the soil profile. If you take the vertical section of the soil, which we can define soil profile, and in this we see the vertical variation, then top layer which is the darker, and then less darker layer, and when you will reach the lowest layer, which is called sea layer or sea horizon, that is known as a parent material. So this vertical variation, we want to, if we want to characterize the soils, then we want to know the soil variation from the sea horizon, because this is the parent material over which soil has been formed. Then why this material becomes dark? It is because of the interaction of climate and organism, and some of the material is moved from this layer to the subsurface layer, and that's why it becomes also change in the color. But the last layer, sea layer, is unaltered, which is remain very much unaffected by climate environment. So the movement of the soil particles, organic matter, salts concentration from top to bottom depends what is the condition of the soil, because it depends on the slope or topography. It depends on the type of climate, means arid area or humid area. It depends on the what vegetation is growing over that. All these factors governs the physico-chemical properties of the soil. So that is the vertical variation. And then another variation is known as a horizontal variation, and horizontal variation lateral we see that one, but here we describe the soil up to the 2.5 or 2 meter depth, which is near to the sea layer, sea horizon. Here in this slide it is shown the concept of the soil mapping. You see this picture is this is known as a padon. Padon is a where we are seeing the various horizons, and this is also known as a soil profile. This soil profile we study, but we want to map this padon where up to which area it is extending. Then we need to demarcate our land or our area into various land area or into various unit. We call it is landscape unit. Each landscape, this landscape is represented by padon, which we study in the field. But this landscape, how to characterize, that is based on our remote sensing data analysis. Remote sensing help us to delineate landscape unit, and once we have delineated the landscape unit, in that any point if we take the soil profile, that soil profile will represent soil of entire landscape unit. And we say here the one landscape unit is composed of many padon, and those padons are similar in characteristics. That's why we call it is polypadon. So we can say padon is the unit of the soil sampling. Padon is a soil sampling unit, and polypadon is a soil mapping unit. We can map polypadon, we can characterize or we can study padon. So to map polypadon, you have to delineate your area into landscape unit, divide your area into landscape unit based on remote sensing data, which I will discuss further. So in a soil mapping, what are the steps we do? First, characterization of soil. We take the soil profile, we characterize its morphological characteristics, physical characteristics, chemical properties. Morphological means color of the soil, depth of the soil, and coarse fragments or structure of the soil. Physical properties, you know, the bulk density, texture. Chemical properties, pH of the soils, electrical conductivity, nutrients present in the soils. So we characterize. Based on these characteristics, we classify the soil. The classification is also very systematic. We use standard classification system, that is soil taxonomy. Is a one classification system. With that, which is developed by US Department of Agriculture, we use for the classification. Once we classify the soil, then we map this soil present where. Then using remote sensing data, and then we plot the boundaries on the base map or topo sheet, and that becomes the soil map. But soil map is incomplete unless you don't make its prediction. The soil is useful for what purposes? So we make the prediction, that is known as a land evaluation. Soils are prepared of three scales in general. One is the detailed, which is prepared at 1:20,000 scale. Semi-detailed, standard scale is 1:50,000 scale, and reconnaissance survey or reconnaissance soil map, which is 1,02,50,000 scale. You see the remote sensing data for detailed scale, high resolution remote sensing data, Cartosat 4, Cartosat 1, 2, list 4 are used. But in 50,000, list 3 data and Landsat TM data, which is the medium resolution sensors are used, and 250,000 IRS list 1, list 2 or WIPS data are used. So here is the coarse resolution satellite data are used. This 1:250,000 scale for the entire country soil map has been prepared by National Bureau of Soil Survey and Land Use Planning, NBSS and LUP situated in Nagpur, and 50,000, around 2/3 of the country has been mapped at 1 is to 50,000, but many part of the country systematic survey has been not done, has been not completed, and detailed very few area has been mapped at 1 is to 50,000. But for our project purpose, many times we need maps at 50,000, at 20,000 scale, which are in general not available. Then question comes, how we prepare this map? So in this lecture I will discuss, that is how you can prepare soil map at 20,000 or 50,000 scale. The procedure is that first of thing, that you select a satellite data of correct resolution, means higher resolution sensor data is required for the detailed soil mapping, and medium resolution sensor is required for 1 is to 50,000 soil mapping. So before process to the how soil mapping is done, we should know what are the soil forming factors. Soil forming factors, because any place the development of soil depends on what are the factors responsible for development of that soil. So we should the basic concept behind soil mapping is based on the soil forming factor. The first factor which the Jenny, one scientist, given the factors described in 1941, and till today it is being used as a for studying the soil. He told that soil is the function of climate, organism, relief, parent material, and time. Climate, which is temperature and rainfall, is important. Organism, land use, land cover. Organism describe the land use, land cover. Although in the soil, the organism means microorganism and macroorganism. Microorganisms are fungi and bacteria, which are not important for soil resource mapping. Macroorganism means land use, land cover is important. These factors are active factor. Why we are calling it is active? Because active factors are those factors which provide energy to the system. So these active factors provide energy, and three factors: parent material, which we can describe with the help of geology, landform, relief. Fourth factor, which we can describe with the help of topography, means slope and aspect of the region. And third is time. Time is the period when how much time is taken by the soil in weathering or from development from rock to the stage of maturity. And these three factors are considered as a passive factor. These passive factor means these are the factor which condition for the development of the soil. So our soil mapping concept is based on all these five factors. And for any area, you can say, suppose for any area, if we want to map, suppose you are want to map one watershed or one district. So for it, you can consider climate and time. These two factors you can consider as a constant, which is not changing much, because here climate means major change. For example, arid climate, semi-arid climate, tropical climate. So in a one, if area is not very large, you are not going for regional mapping, you can consider climate and time as a constant for time being. Then there are only three factors left which are governing variability of soils in your area. First is your first factor is parent material. So parent material, how I can identify? Then you need to prepare the geomorphology map with the help of remote sensing data, or when we are using the standard FCC false color composite. With this one, we can map geomorphology of our area. You know, for example, in one area, maybe the geomorphology, maybe your hills, foothills, alluvial plains, or your area is completely alluvial plains, then there may be old alluvial plains, young alluvial plains, flood plains, river channels, like that one. So we first identify the geomorphology, different type of geomorphology in your area, and that will tell about the different type of parent material present in your area. Then this geomorphology you divide based on the topography. See the topography, or topography means slope. Based on the slope you divide, and then you will make the combination of parent material and slope, that is I am telling here geomorph and slope, and this further you divide the area based on your land use, land cover, which is comes under organism. So then you will get then you will get one unit or land polygon, which we call it is a physiographic unit, or you can call it is a landscape. So I told you earlier that landscape division is the we require to prepare for soil map. So first we have to identify the landscape. How you can identify the landscape? Then simply I will summarize that first you divide your area into geomorphology, then each geomorphology you further divide based on the slope, and then geomorphology and slope unit further divide based on the land use, land cover. For example, which area is under forest, which area is under agriculture, which area is under scrub land. So that division will form the polygon, will be called landscape, or it can be also called physiographic unit. And this area, you can say, in this area soil forming factors are same. So in that polygon, every place the area soil forming factors are same, then we consider the every point soil is same. So any point, any place, you take the profile and you characterize, that will denote the characteristics of the entire landscape unit. So thus I can say soil mapping requires delineation of physiographic unit. Here you can see with this example, this is one area. Here I have divided the area based on for the parent material first. So there are three types of geomorphology. One is the hill, this is the foothills, and this is from here to here, it is alluvial plain. Why I am saying alluvial plain from this to this place? Because you see this is the river, and in the river you are saying there is a water appearing on the surface, blue color. So from why water is appearing from this place? Because from this place the material has changed, geomorphology has changed, and that's why this area coming as a darker tone, and this is the alluvial plain. Remote sensing data only can help you to demarcate the alluvial plain, foothills and hills very clearly. You see the hills boundaries are going like that one. This is the hill, and this is I have divided, this is the hill, foothills and alluvial plain. Then second stage, you divide your each geomorphology. Suppose this is the hills or Shivalik hills. You can divide these hills into slope classes. I can see from here to here one slope, and from here to here another slope. So this is steep sloping, it is the moderate steep sloping, divided into two. Now third variation is, I told you, the organism, land use, land cover. You see the entire area is forest, then I can say the entire area is the forest in the Shivalik hills with the steep sloping. So every place the same soil forming factor, here and here the soil forming factors are same. So I can say that for the entire area soil is only one type. So you can take sample any place, and that will represent the soils of this entire area. Similarly, this is the Shivalik hills, moderate slope with forest. Here you see this is the foothills, Piedmont plain, and here you can see entire area is gentle sloping, slope is not changing, but this area is under cultivation, agriculture, and this area is under forest. So soil in the forest and agriculture will be different. So I have divided the Piedmont based on your slope, based on your land use, land cover, that is forest cover and agriculture cover. Now this entire area you can see the agriculture, it is under agriculture of Piedmont plain with gentle sloping. So any place you take the soil samples, that will represent the soil of the entire area. That is the basic concept for soil resource mapping. Similarly, you see the one area of the Goa terrain. You can see from the remote sensing data, FCC is draped over 3D 3D view. You can see of that area. This is the hill ridge. One hill range is going. You can see this is the another hillocks. His top is the flat, but between the two hills, that is the valley area. So I can divide my area into the various geomorphologic unit, that is the hills, generational hills, valley, and here along the river terraces. So my submission is that first of all you divide your area into geomorphologic unit, and the geomorphology further divide based on the slope. So suppose this is the hills, top of the hills, but it is the side slope of the hills. So you interpret this one and you interpret this one separately, and then you divide based on your land use, land cover means forest, agriculture, barren, because soil in all land use will vary, and this can be interpreted into the so I can say that is the steps which we follow for the soil resource mapping is: first we do the visual interpretation, second we do the ground truth collection, go to the field and take the soil profile, then third, come to the office and what the samples you have collected, you analyze that one and do the, and we know it is a post field interpretation. So in ground truth data collection, we take a sample strip, or we see from top to bottom, means highest area in your landscape to the lowest area. You take the sample at every place, you do the detailed survey, take the samples very close interval, do the soil profile and collect the soil samples for the soil analysis, and then like that one we go to the field. This is the hill and side hills. I was showing you the side hills, and in this take the soil profiles, and here you can see the top A layer and you C layer. You see the difference in color. If color is changes, it means organic matter and other properties are changing. So we collect the samples from the A layer, B layer and C layer, and we analyze the soils for classification of that one. But near to the hills, when I have taken the soil profile here, just near to the hills valley area, you see the soil profile, soil has changed. So this profile is showing that water is there in the soil profile. So in the valley fields, having very depth is very high, but water is appearing, drainage is poor. But in the hills, you are saying that is no water logging condition, so drainage was not poor. So like that one, we characterize the soils and we prepare the soil map. So post-field interpretation includes characterization of the soil profiles, and then we classify the soil based on soil taxonomy, and then we prepare the fresh boundaries. We delineate the landscape unit, which is known as a physiographic unit. So again you prepare and make it final, and after final, then you can say the soil resource mapping composed of these steps: preliminary visual interpretation, then you do the ground truth in that units, take the soil profile, soil sample, and then you do the analysis, then you do post field interpretation and prepare the soil map, and this will, you can convert it that area by visual interpretation. You have prepared so much of map unit. This is physiographic unit, and when you will add the soil information in this physiographic unit, then it becomes physiographic soil map. So with the remote sensing data, we interpreted physiographic map, and physiographic map means it describes the geomorphology, first factor, then topography, second factor, then third is land use, land cover, divided on that one. You see here, this is the hilltop, where you are seeing the black color means is there was the barren area, but here the green color is the forest area. and light green is the scrub area. And you see the red color, what is shown, that is the valley fill. Red color is shown here, you see the VF valley fill. So between the two hills there was valley fills, and these characteristics I can very well see in many places the valley fill. One place or two place I will describe the take the soil profiles in the valley fill, and based on that characteristics for everywhere there is valley fill, I will assume the soil is same. So advantage of remote sensing is that for the large area you can interpret the physiographic units, and few sample area or few units you can characterize the soils, and you can prepare the map for the entire area. So this interpretation is the you can achieve by visual method, not digital. Operational technique of soil resource mapping is the visual technique, and because directly remote sensing data directly do not give the information about the soil, because the soil we are interested in the subsurface information, and remote sensing data give the reflectance of the surface characteristics. So we cannot map only the, if we take the surface reflectance, it will show only the land use land cover, not the differences in soil. So for soil mapping you need to interpret systematically, first the geomorphology, then the topography, and then land use land cover, and what it is prepared, this is the physiographic unit. And this methodology is irrespective of your scale. Either you are preparing 50,000 or 250,000, any scale you will do the same methods of analysis. It is not related with the scale, and you will prepare the physiographic map, and then in that physiographic unit you study the soil profile, collect the sample, and you can prepare the soil map. And in this soil, in this map you see there is a valley fill, there is a dendrocenal hills, like that one you have designed, and each unit then you will give the characteristics. For example, valley fills, I have seen the texture is loam, clay loam, soil depth was more than 40 centimeter, but drainage was imperfect, erosion was even, pH taken from the soil is 6.1. So you can say this valley fills having these characteristics. So these characteristics are based on the soil profile. Similarly, for all map units we make the soil characteristics a table, and this table you can link with your soil map. Then now you have prepared your soil map, and now you are interested to assess the suitability of soil for various purposes. So soil map used for various purposes, and we do the land evaluation. Land evaluation is the technique where land evaluation is required for the land use planning. We want to assess the suitability of land for various purposes. For example, forestry, agriculture, urban, watershed development, or any landslide study, or water resource study, reserve, that is recharge zone area identification. For you want to use this soil map for interpretation purpose. Here my presentation is restricted to the map for preparing the land use land cover, land use planning. What do you mean by land evaluation? Basically, suppose we want to study that is this land is suitable for forestry or not. Then we take the characteristics or requirement of the forestry, and we know about soil and land characteristics of our soil. We match both the criteria. Suppose forestry requires soil depth is more than 100 centimeter. If my soil is only 20 centimeter, then I can say that place forestry cannot be done. So depth, texture, pH, many properties of the soil is taken, and the same properties requirement of the forest is taken, and both are met, and we study the suitability. If they are suitable or not suitable, then we recommend as a land use planning. So this is the basic concept of land evaluation. Generally, three types of land evaluation is carried out in field of agriculture. One very common is land capability classification. Second is land irrigability classification. Third is FAO framework of land evaluation. I will discuss these one by one. Land capability classification is assessed to analyze the inherent physical potential of the land. Inherent physical potential of the land to support land use without degradation to land and water resources, means for sustainable use. The land is divided in this. There are 8 land capability classes. Class 1 to 4 we call it is suitable. If your land is coming class 1 to class 4, then the land is suitable for cultivation. If it is coming class 5 to class 8, then it is unsuitable for the cultivation. What are the reason by which they are unsuitable for the cultivation? Then we that decided by the factors. Which are the factors are there? Maybe because of the wetness or more water, maybe because of climate, maybe because of soil or erosion. So these are known as a subclass. Basically there are 8 land capability classes. Then how we do the land capability? Here you have the soil map and soil characteristics. Here you have the characteristics of the land capability criteria. You can match both and you can prepare the land capability classes map. So class 1 land is most suitable for agriculture, and class 4 is having the very severe limitation. So class 1 to 4 limitation increases and for the agriculture purpose. But if it is coming class 5 to 8, it means it is suitable for forestry and pasture land. Class 5 land is most suitable for the agriculture. There is no limitation of for its use for the forestry purpose. Class 6, class 7, class 8. Class 8 is the land very steep sloping, stony, barren, which comes with the last category of the in the forestry application. So you can prepare the land. That for that soil map you can convert soil map into land capability map, because you have the characteristics of the soil and you match with the criteria of land capability, and you can find out different soil belongs classified into which capability class. So you can see here that is yellow color showing capability class 2, or here red class is showing capability class 6, which is suitable only for the forestry purpose, not for the agriculture purpose, like that one. Soil and land irrigability, we want to assess our land is suitable for irrigation purpose or not. So soil and land irrigability, for that one we use the soil irrigability classification. Soil is classified into A, B, C, D, E, 5 irrigability class, depends on the soil depth, soil texture, soil chemical properties. All are taken in physical properties of the soils. On the basis of that, we classify the soil into 5 soil capability class, irrigability class. Then based on the soil irrigability and land characteristics, we go for the land irrigability class. So land irrigability class, you can classify class 1 to class 6 based on its characteristics, and you can see this is the land irrigability class. Land irrigability, so irrigability class 2 shows yellow color, only this land is suitable for the irrigation purpose. Red color shows that is it is 4th category, this land is not a very severe limitation for the irrigation purpose. So we can decide where we should do irrigation for sustainable agriculture. Then third evaluations we do for FAO framework of land evaluation. This is the most widely used method for assessing the suitability of land or soil for our crop purpose. Suppose I want to know my soil is suitable for wheat crop or it is suitable for the maize, gram crop or any pulses, then I have to match the requirement of the crop and what the type of soil is there, and by this one I can find out this land is suitable for which crop, and it is based on this FAO framework of land evaluation. We classify this area it is suitable or not suitable, that is the order. Then we say this is suitability class, if it is suitable, this is most suitable, S2 moderate suitable, S3 marginal suitable, and 1 unsuitable. So these we have the criteria for all type of suitability, and we match one by one that it is coming with which suitability, and then we decide this map unit is this map unit or landscape unit is coming which suitability class, and we decide the suitability. We can do for the suitability for various crop. For example, it was done for paddy, sugarcane, cashew, coconut, and we find that is suppose valley fills where you have seen the water into the soil. This is the for the paddy it is moderate suitable because paddy require water, but for the sugarcane it is marginal S3 suitable. It is not very good suitable. So in valley fill area, my choice will be to for the paddy crop, not for the sugarcane crop. But in CP coastal plain land, I find paddy is also S2 and sugarcane also S2. Then I can say I can take any crop among them. In both class crop I can select any crop there. So that is the way of that selecting the crop, that which crop I should grow in my area. This is then you can prepare the suitability map of your crop. Then after land use planning, we can also use remote sensing data for mapping of the degraded lands. What do you mean by degraded lands? Degraded lands are the land which lost, where you find the decline in the soil quality, which is caused by through the misuse by the human. Because when we are using the land for irrigation purpose, we are developing or taking extra agriculture or extra crop, then you are over exploitation of your natural resources, and that will trigger the degradation of your land. And land degradation you can divide into three types: physical degradation, chemical degradation, and biological degradation. Physical degradation, erosion, water logging, soil compactions comes under that. Chemical degradation, when the salt becomes a high amount in the soil, that is salt affected soils or soil acidity, which is chemical degradation. And in your soil, if organic matter is less or becoming less, then it is biological degradation. In India, our 80% of land, of the total degraded lands in the country is 120.72 million hectare. This is the statistic given by Government of India, ICAR, ISRO. Every organization have with consensus they map the area 120 million hectare land is total degraded, and out of 328.7 million hectare land of the country, in 120 million hectare, 80% land is affected by water erosion. So you can see that is water erosion, 73 million hectare in agricultural land and 9 million hectare in open forest area, and you can see the different area statistic of the degraded lands. You can see the satellite data how we can map the degraded lands. As I told you, the water erosion is the main cause, or 80% land is degraded because of the water erosion. You can see the degradation. You see the here you are seeing the lot of dissected lands, cut lands, and this is your very severely eroded. And here you see the crop is there, but it is also plain land, but here you are getting more reflected. Because of erosion, surface organic matter and clay material is lost or removed from there. So because of that, it gives the high reflectance, and it deposited in here the lower ridges. So here you are getting the accumulation of clay and organic matter. So good crops is there. So it is slight erosion, it is moderate erosion, and it is severe erosion. So you can map erosion through directly, you can see from the satellite data, but indirect or you can interpret it with the help of the topography, with the help of the vegetation features, different type of erosion. Salt affected soils, or I told you that is the chemical degradation. In irrigation command area, because of more irrigation, what happens, the salt present into the soil, they come to the surface in arid climate. In arid and semi arid climate, Haryana, Punjab, Rajasthan, in the irrigation command area, the salts gets salts are present in the soils at the lower level, but due to heavy irrigation, the salts gets absorbed, and by the capillary action they come to the surface, and you can see the white color here because the salt deposited on the surface. And in the May month or April month, they give the maximum reflectance, and blue, green, red radiations all get reflected in equal amount, and they appears on the remote sensing data as a white color. And waterlogged area also appears in that one light greenish blue or bluish green color. So these are the waterlogged area, and these are the salt affected soils, and these are the cropland. Crops are standing. So you can see that is salt affected soils from the satellite data very clearly. Then if we see the spectral reflectance characteristics, then you can see this is the normal soils give the reflectance high in this band, but in you see that is the saline soils or strongly saline soils, they give the reflectance than your normal soils. That's why they are appearing in white in color on the standard false color composite, and we can identify the saltwater soils very clearly on all remote sensing data. This is the irrigation command area of the Rajasthan, that is Indira Gandhi Canal command area in Rawalsar district. You see this is the canal is coming, and along the canal the bigger this you are seeing irregular shape of the waterlogged area, and places in patches where the depressional lands are there, water get collected there, and it is appearing as a water body. This is the waterlogged, but near to this waterlogged body, this land is also having water at the root zone. Means if we dig up the soil profile here, just after 30-40 centimeter, you will get the water there. It means water is appearing to the surface. And if you will go irrigation and irrigation, the entire land may become the waterlogged land. And you can see that in list 4 data, this is the waterlogged area, and this is the salt affected soils. So in this one, and here you are seeing this one creamish color, this is the sand dunes. So sand dunes are there up having higher elevation, they are appearing that is your creamish color. But this white color is you are seeing that is the salt affected soils. This white color patches are salt affected, and most of the area is waterlogged area. So this waterlogging conditions, waterlogged and saltwater soils can be met with the satellite data. Here remote sensing data you can also use for monitoring of the waterlogged land. Here you can see one example, that is in 1975 the same area, and in 1995 what appears, you can do the monitoring, waterlogging is increasing or decreasing. You can see in 1975 this much is the this is the here waterlogging was less, but in after 10 years 85 you see the waterlogging condition, it is appearing like a channel. Here it was no waterlogging, but in 90s you can see that area has converted into waterlogged and like a channel, and in 95 after 10 years you see that it becomes like a lake because you are seeing the bluish color. So this type of monitoring also can be done with the help of the remote sensing data. We can use hyperspectral remote sensing satellite data also for the mapping of the soil properties. What the earlier examples I have given, that is your using multispectral satellite data, 4 band or 6 bands, but you know that is in coming generation or in future we will have a hyperspectral remote sensing which will having 100 to 200 spectral bands. And what it will be have the advantage that hyperspectral remote sensing will help you to characterize the chemical constituents present into the soil, or you can analyze the soil properties quantitatively, or you can map the soil nutrients using hyperspectral remote sensing data. Multispectral data, you can do the qualitative analysis. but with hyperspectral remote sensing data, you can do the quantitative analysis. So here it is, but hyperspectral remote sensing, there is one more crucial requirement is that you have to do the atmospheric correction of data. You see the uncorrected data appearing like this one, but this data was when corrected, it was appearing showing more variation, and we for each we for any point for example salt or for any constituents, we generate the spectra how salt spectra is coming. So with that help we can map the salt concentration or quantity of the salt present into the soil. Here you can see the Hyperion data was taken of 240 number of spectral bands, and here we have taken the soil samples in one area. Our objective was to map the soil carbon because soil carbon is one of the most important properties present of the soils. If you have, you know that if soils are having more organic carbon, you can say the soils are more productive, and this soil is supposed to be good. So we used to map the organic carbon with the help of your remote sensing data. So for what we have taken, first we have taken the samples in the entire area and make the correlation analysis, that is which band we are getting very good reflectance of the organic carbon. So we find the three spectral bands, 681 nanometer, 569 nanometer, 487 nanometers, giving the good results. Then using these bands we prepared the index, brightness index, saturation index, hue index and coloration index. These three indices, which the formula is given here. Using these indices and the indices value and soil carbon value was made the correlation study, and we found that is saturation index and brightness index having good correlation with the soil carbon. So using this index we can map the soil carbon in the study area. Another, suppose in the soils clay mineral is, which type of clay mineral is present is very important to study the fertility of the soils, nutrient of the soils. Different in the soil there are different type of clay minerals. You see here calcite, kaolinite, montmorillonite, hematite. And these minerals, which mineral, if in your soil montmorillonite minerals is present in high amount, then we can say that soil is very good for the agriculture point of view. But if it is kaolinite is present, then it is not so good, because montmorillonite have the capacity to hold lot of nutrients into in this mineral, so it provides more nutrient to the crop. So if we want to map the fertility of the soils, then we have to map the clay minerals present in the soils. So you see in one study the clay minerals montmorillonite, you can see it is present here. I can see where the montmorillonite is there, the soil fertility is very good, it will, their crop performance will be very good. And kaolinite is present here, which shows that the soil performance will be poor. So clay mineral mapping, soil organic carbon mapping, soil salt concentration mapping, these in individual soil properties, its quantification can be done with the hyperspectral remote sensing data. So I can conclude that remote sensing data provides you a reliable information of the soils, and there is no other tool by which you can prepare the soil map. First of all, you have to prepare the soil map by systematic interpretation, deriving the physiographic units. You can study the soil forming factor with the help of the remote sensing data, and this remote, and then you can use the remote sensing data for mapping of the degraded lands, and then you can prepare a database in GIS which will help you in effective management of your soil resources. Thank you, and for your questions you can ask.